Hi, my name is Alyssa Murphy, and this is my presentation for Lab 1 Constant Motion for Physics 2211, Section W02 at Georgia Tech. So starting off with a brief table of contents, first I'll be going over an introduction to this lab, then the experimental model I created, then the computational model I created, then an analysis of the possible sources of error in the lab, and then finally answering the what if and what does it mean questions. So starting off with a brief introduction, the purpose of this lab is to demonstrate the differences between an ideal model of constant velocity and a real-world example using Newton's laws of mechanics. The concepts that will be touched on in this lab are constant velocity. So an object is considered to be at a constant velocity when the net force acting on the object is equal to 0. And this is related to Newton's second law, which states that a change in velocity occurs when a force acts upon an object. So what we'll see in this lab is that there is no net force acting on the object, so that change in velocity does not occur. The set of equations that will be used, the momentum principle, where the change in momentum is equal to the net force times the change in time, velocity update, which is the final velocity, is equal to the initial velocity plus the force times the time. So this one shows, again, that without that net force, there will be no change in velocity. And then position update, which is the same as velocity update, except V average is used instead of F net. And then average velocity is calculated with initial velocity plus final velocity divided by 2. So, brief introduction to the results. After creating the physical and computational model, the computational model was more accurate to the intended motion of the lab, as the graph created was more linear. So then going into the experimental created using tracker. So the system in this experiment is the orange ping pong ball that was used as the object. The surroundings is everything else present, the desk, the air, me who's pushing the ball. And then the initial conditions, I set it so that the tracking only begins once the ball is actually in motion. So here's the video. And then moving on to the computational model, this was created using GlowScript, like VPython. And essentially, I just edited the starter code. So I kept the mass the same as there was no change in force. So there was really the mass was really irrelevant to the calculations. And then I altered the initial conditions. I altered the initial velocity, ball.vel, to be the calculated average velocity. And I calculated this average velocity by doing the final velocity plus the initial velocity divided by 2 of the tracker code, or the tracker from the experimental model. And then for the second part of the code, I kept the net force the same because there is no net force, and then I only changed the updating of the object's position. Again, I altered that to the calculated average velocity. So then the graphs created using GlowScript. The top one is position versus time. This position versus time graph is linear, which shows that the net force is 0 and the velocity is constant, which we then see on the velocity versus time graph with that straight across line showing that there is no alteration of the velocity. It stays constant at 0.0024 meters per second, which was the calculated average velocity that I mentioned earlier. So this is the comparison graph. The blue line represents the experimental model and the orange line represents the computational model. And then there's the calculated R-squared values. So based on those R-squared values, the computational model is more accurate because it has a value closest to 1, which is perfect linearity. And the experimental model seems to have a slight curved growth, indicating that there was a small net force present. Granted that, however, the experimental model did have an R-squared value of 0.9947, which is very, very close to 1. So then some possible sources of error in this lab. One of them would be the tracker video errors. As I was placing the tracker on each frame, I was not necessarily placing it exactly in the middle of the ping pong ball, which would lead to either a too small or too great update of the position, which would show a velocity change that was not there. And then there were some initial movement errors. Because I placed an external force on the ping pong ball to put it into motion, the net force was not exactly 0, which would cause changes in velocity and is likely what made it so that the experimental model graph was not exactly linear. So then going to the questions, the what if question asks us to consider what the results would look like if the axes were flipped in the tracker video. So if the x-axis was flipped, the ball would be appearing to move in the negative x direction instead of the positive x direction, and the graph of position versus time would slope in the other direction for the experimental model. GlowScript would need to be altered to have a negative velocity to counteract this, but the relative slope of the graph and the linearity would remain the same. And then for the what does it mean question, we're asked to consider if it's possible to determine which forces are acting on the observed model. So I'd say it's possible to consider which types of forces are acting, but not necessarily how much each force is contributing to the net zero. For example, we know that my hand gives an external force in positive x direction, and the frictional force gives an external force in the negative x direction. However, we don't know just from observation how much force each is contributing. Hypothetically, the forces on the ball would be the external push that I gave the ball, frictional force, gravity, and the normal force. Thank you so much.